Okay, thank you for coming, everyone. So we have a very exciting lecture today from Jules Jacobs, who is currently a postdoc at Cornell and did his PhD at Radboud University. Jules works on a bunch of formal methods, type systems, semantic concurrency issues, and programming languages. And he's a fantastic writer. I just completely blown away by his first paper and used it for a ton of material in my special topics course I did. So hopefully I haven't set up too high expectations. Go ahead and take it away, Jules.
Thank you, Gilbert. Yeah, today I want to talk to you a bit about my PhD work, which is about creating deadlock-free languages. And the main point of these languages is that deadlock freedom is guaranteed by construction. So any program you write in these languages will be deadlock-free. So we achieve that by co-designing the language with a formal verification method. And I want to first talk a little bit about another success story that uses this methodology, which is Rust. So in Rust, you get memory safety by construction. So if you write any Rust program and it type checks, it's guaranteed to be memory safe. So this is nice because you get some correctness property that you don't get in other languages like C++. It rules out a certain class of bugs, like you don't have buffer overflows, at least not the ones that create security vulnerabilities. You don't have use after free, and all kinds of other issues are resolved. But at the same time, we retain performance in Rust. So it's not like switching to a garbage collected language. You still keep roughly the same performance as C++. In particular, because the verification is done at compile time, we don't have any runtime overhead. And this point is maybe a bit debatable, but I claim it's still quite usable, at least compared to other ways of ensuring memory safety formally. So if you were to ensure memory safety by very carefully reading your C++ code, I claim that's less usable than a tie system like Rust. In fact, in Rust, you get a really strong formal guarantee. If you wanted to get the same formal guarantee by hand, that would require doing some massive mathematical proof. So what I want to talk about today is applying the same methodology, but not to memory safety, but to deadlock and memory leak freedom. So let me first set the stage by talking about the history of programming languages. So I left a few languages out, by the way, but at the beginning we had systems languages like Fortran, C, C++. But in 1991, we got a more high-level language. And of course, I'm forgetting languages like Lisp now. But from that point on, we got a lot of languages that are high-level. And then I classify these in two groups. One is the systems languages, and the other is the, let's say, the high-level languages. And these have some properties. For example, in the systems language, you do manual memory management. In the high-level language, you do automatic memory management. The systems languages are low level. These languages are high level. The systems languages are unsafe, so you can easily write a bug that creates a security vulnerability. On the right, it's safer. It's hard to write a program that lets an attacker overwrite anything in memory. That only happens if you use some unsafe API. And so there are a bunch of other differences. And I claim Rust doesn't fall into either of these categories. I put it in its own category. And I call this here the ownership category, because in Rust, the type system tracks ownership over data, whereas in the green category, the ownership is tracked at runtime by a garbage collector, and in the yellow category, it's tracked by the mind of the programmer themselves. So how was the Rust language created? Actually, there's a very long history, which goes all the way back to Girard, who was basically a mathematician. He developed something called linear logic. Later on, this was put into practice in programming languages land, actually at Cornell at the time, by Greg Morset and others, building this language Cyclone, which is a version of C that has Rust-like properties. So I claim Rust is basically a marriage of Cyclone and other languages like SML. So today I want to ask, okay, what comes after Rust, but still in this same new blue category? So let's look at the Rust guarantees. So we get these kind of guarantees like no use after free, no null pointer exceptions, no memory unsafety, no data races, interestingly, no stack faults. But we do not get deadlock freedom, and memory leak freedom. So actually, initially, the Rust developers thought they were going to get memory leak freedom also. And they had a function in the standard library called, I think it was called leak at the, or memforget it's actually called now. And what that function does is it takes any value and leaks it, so the type system no longer tracks it. Initially, they marked this function as unsafe because they thought that in the safe subset of Rust, you couldn't write a memory leak. Later on, they realized that actually you can just write a safe Rust function that leaks any value. And then they decided, OK, there's no point in marking this function as unsafe anymore, since you can just implement it in safe Rust. So what about deadlocks? I think nobody believed that Rust was deadlock-free. But in fact, in practice, it is a problem. So here are two studies, one in Rust and Go. And in both cases, they found that 50% of concurrency bugs were deadlocks. In fact, the authors of the Rust study say the following. They say deadlocks are a bigger problem in Rust than in other languages. So why is that? What do they say? They say even though problems like double locking and conflicting lock orders are common in other languages as well, Rust complex lifetime rules, together with its implicit unlock mechanism, make it harder for programs to write blocking bug-free code. So what do they mean by this? They mean that in Rust, if you acquire a lock, the type system and the compiler decide where to unlock the lock, where to release the lock, because it's implicitly where you last used the value that was protected by the lock. So in your code, there's no apparent point at which the lock is released. This means that it's harder to make sure that your code doesn't deadlock because you don't actually see where the lock is released. So this is why they believe it's more common in Rust than in other languages. OK, so let's now design a language without deadlocks. And the point is that deadlocks then cannot compile. So talking about this co-design of languages with verification, I first want to change the lock API with respect to Rust. I want to use a different API, which will be necessary to make this thing work. So here are the 5 operations. So the first operation just creates a new lock. So it does not acquire a log or anything. It just creates some data structure in memory that represents the data of the lock. And like Rust, these kinds of locks that we have here store a value inside of them. So it's like you can imagine a box that you put a value into. So this is different than logs in C, where logs are just a thing on their own. And the data that is protected by the lock is managed separately. Here we really put the data that's protected by the lock inside the lock using an explicit release call in this case. So if you do l.release v, it puts our value v in the lock. On the other hand, acquire, if you call acquire, we get the value v back. And note that acquire is a blocking operation. So if there's currently no value in the lock, then acquire will wait. And then we have 2 remaining operations. One is drop, which just drops our reference to the lock. And we have wait, which waits until all the other people who have a reference to the lock have dropped it. And then we get the value back out. OK, so let's see an example right here. We have this example code here, which creates a new lock. Initially, the lock is already acquired in this API. So what we first do is we release the lock and put the value 1 in it. Then we spawn 3 child threads that are all going to increment the value in the lock. At the end of the day, the main thread is going to wait and print the value. OK, so let's see how execution works. So I use this blue circle to represent the thread here. So this blue circle is the main thread. So the first step that's going to run is this lock creation operation. And this is going to create this box in memory, which is currently empty, which represents this variable, which is pointed to by this variable L. When we release, the thread puts a value 1 in the lock. So now the box contains value 1. Then, as the next step, this loop is going to run 3 times. So we are going to spawn 3 child threads. Let's spawn them right here. And they all have a reference to the lock. Now let's see what the first child thread is doing. Let's suppose the scheduler decided to run it first. So let's the top one in this case. So it's first going to acquire the lock, which means it's going to take this value 1 out of the lock and keep it to itself. Then it's going to release the lock, but with an incremented value. So it's going to increment its value and put it back as 2. And lastly, it's going to drop. So it's going to drop its reference, and then that thread is done, so it's going to exit. So the same thing is going to happen with the other threads. It's going to increment, exit, increment, exit. Now we arrived at the wait statement in the main thread. And note that this wait statement was blocked all the time because there were still outstanding references to the log. So it couldn't proceed. But now it can proceed because everyone is done. And we deallocate the log and get the value 4 out. OK, so now I want to ask, OK, is this language now deadlock free? No, it's actually clearly not. But let's see an example of that. Let's suppose we change this final wait statement to acquiring the log and then dropping it. You might think that's the same. What wait does is just takes the value out and then drops the reference. But in fact, this program can now deadlock. So why is that the case? Suppose that the scheduler unhappily decided to schedule the code after the loop first before any of the children are scheduled. In that case, you would get the following situation. So the main thread acquired the log, so it took the 1 out. And then it dropped the reference to the log. So now the main thread is, from its perspective, done. But the other threads are now blocked indefinitely because the log is never going to be released by anyone. OK, so the language is clearly not deadlock free. Well, let's make it so by adding a type system to the language. So we want to make sure that if deadlock is possible, then the program is ill-typed. So here are the formal rules for the type system. But actually, as far as type system rules goes, these are really simple. But let's not look at those. Let's look at it by example. So let's look at a couple of deadlocks and see how each of them is fixed. So here is a very simple deadlock. We just acquired a log twice in the same thread. And I've actually heard complaints about this from a friend. He says, Rust is the only language in which I've made a single-threaded program deadlock. And well, he basically did something like this, but more complex. And the reason is actually that in Rust, in order to have a mutable global variable, you have to put it in a log. OK, so how are we going to prevent this? Well, we are going to use the following rule in the type system. So initially, this log is, let's say, a log of int, because you're storing numbers. Then after this acquire, the type system is going to put a key in the log type. And this key means that currently this reference L has acquired a log. OK, so this is basically a Boolean that's being tracked in the type. And then when we call acquire a second time, it's not the type system is going to say error. We already have this key there. We already have acquired this reference, so we cannot do it again. OK, so this key is going to prevent this kind of silly deadlock. But now let's try to work around that. And let's try to acquire it twice anyway. So let's say what we first do is we say L2 is L1. Note that according to the normal typing rules, both of these are of type log of int without a key in it. Now we acquire the log via the reference L. Now that reference L is going to get a key in its log. But the type system doesn't know that L2 is actually the same as L. So in this case, you would think that this is going to be allowed. So we're just going to take a big hammer and disallow this by saying, you cannot copy a log. OK. So let's now look at another deadlock that could happen. Suppose we acquired a log. We released it. A leak that can happen, because we're also going to rule out memory leaks. So here is an example. We acquire a log. We release it with a value, and then we drop it. According to how the memory management works, this log is now never going to be deallocated, because drop dropped its reference, and only wait deallocates the log. So how are we going to prevent this? We are going to put another emoji in the type, which is the crown. And the crown represents, I am the owner of the log. So I am responsible for doing wait. So when you create a new log, we are the only owner, so we do get this crown. Note that when we release the log, the key disappears, but the crown is still there. Now when we drop, the type system is going to say, you cannot drop a log with a crown, because you shouldn't do drop, you should do wait. OK. So let's summarize the rules. First rule is when you make a new log, you get both the key and the crown. Second rule is, if you call release, then you must have had a key before, but you do not have a key after. And this rule works both, whether you have the crown or not. That's why I made this lightly shaded crown there. Acquire is going to be the opposite. You can only do acquire if you do not have the key. Again, whether you have the crown doesn't matter. Then you have drop, which requires you not to have the key or the crown. So you cannot do that if you have acquired the lock, because that could cause deadlock. You cannot do that when you are the owner, because that would cause a leak. Lastly, to do wait, you have to have solely the crown. OK, so these are the rules. But there's actually one rule remaining, which is maybe the most complex rule, which is the rule for spawn. So remember that we had this rule that you cannot copy a lock. But notice what we have to do here. We spawn 3 child threads, and they each need to get their own reference to the lock. So how is that going to work? Actually, the spawn rule is an exception to the rule that you cannot copy a lock. You can copy a lock on spawn, but not in straight line code. So the rule is going to be actually that on spawn, we can pick one lock in scope that we can copy. So we cannot copy more than one lock. In fact, in the real system, you are allowed to copy multiple locks, but in that case, you need to have had them in the same lock group and have an order among the locks. In this talk, I'm not going to talk about that. So let's look at the spawn rules. So here, spawn has many variations because it distributes the key and the crown to the children such that nothing gets lost and nothing gets created. So here in the top left, we start with a lock that has both the key and the crown. We can choose to give the key to the child, keep the crown in the main. All other combinations are also possible. We can even decide to give both the key and the crown to the child or keep both the key and the crown in the main. OK. If we had only one to begin with, then there's just a choice of where to stand that one. If we had nothing to begin with, then both get nothing. All right, so let's look at our example, how that now works. So in the first line, according to the rule, we get both. We get the key because it's acquired. We get the crown because we're the owner. Then when we release, we lost the key. And now at each spawn, we have the choice of keeping the crown in the main thread or giving it to the child. Well, in this case, we decide to keep the crown in the main thread. But what does happen in this acquire line in the child, we get the key because we have opened the lock. And then the next line is going to get rid of it again because we immediately release. Meanwhile, this crown in the main thread traveled all the way to the bottom. It stayed there. And we are allowed to do the wait. OK, so this program type checks and doesn't deadlock. So what is it? Yeah, go ahead.
So how does the spawn, how did you decide, because you've got these options on spawn, how do you decide what happened there? How do you indicate what happened?
One way is to let the programmer annotate which way it goes. Another way is to give this problem to a set solver and let it decide.
Do you actually need SAT here?
That's a good question. I don't know. It's a problem on my mind to think about. It might be an easier problem than SAT. Yeah. It's more difficult if you have polymorphism and other features. OK, so what is the key point of this type system is that locks are still first-class values like any other value in your program. So you can pass them to functions as long as they have the matching type. You can capture them in closures if you want. You can store locks in data structures like arrays and lists. And you can store locks in other locks. So you can, let's say you have an array of locks. You have another lock. You can put the array of locks in the lock. This is all allowed. And some examples of what you can implement with this is you can, for example, implement promises or message passing in user space on top of these locks. So the main restriction here is this restriction that you can only share one lock on spawn. So if you have 2 locks, you have to decide, do I share this one or this one? And the other lock has to either stay in the main thread or go to the child. As I mentioned in the more general system, if you impose a lock order, you can share multiple locks. But we will not talk about that here. So my claim now is that with the rules I have shown, is if there's no type error, then the program cannot deadlock. Or said differently, if a cyclic wait is possible, then the program is ill-typed. So why is this the case? So here's the intuition, is that if at runtime your graph of how threads and locks are connected didn't have any cycles, plus the key and crown rules are respected, then you have no deadlocks. So the main question here is actually not the key and crown rules. The main question is, why can't we have cycles at runtime? So why is that? Let's look at the following situation. Suppose we were running a program for a long time, and this created some kind of graph of many threads and many locks. But we just focus in on this single region, where we have this one thread that has a reference to one lock. And now let's look at an operation that the thread might do, like spawn. Let's suppose the thread spawns. What does this do to the graph? Well, it spawns a new thread, and it does two things. So first of all, the reference to this lock that contains v is copied. So we now have an extra reference to v. All the other references to other locks that the blue thread had, they have to be divided. Either they stay in the main or they go to the child. So this gets distributed as follows in this example. Note that if the graph prior to this transformation was acyclic, after this transformation it's still acyclic. Now let's see what happens if we acquire. Let's say we acquire the lock in this child. Now we have to look at the outgoing edges of the v in the lock. Note that we can have nesting of locks, so the value v itself in the lock can have references to other other locks outside. So let's see what happens on acquire. Well, we move this value v to the child, but note acyclicity of the graph was not impacted. And when we release, we put it back and everything is fine. We could even have put a different value back if we wanted to. Okay, so this is the intuition for deadlock freedom. So we want to formulate this as a formal theorem. So the idea here is that if you have the type checker which checks these keys and crowns, and you have some kind of definition of how programs execute at runtime, you want to prove that this is in fact deadlock free formally. So how did I do that? Well, I formalized all these three pieces in the ROC proof assistant. So you define your type checker in ROC, you define your runtime semantics via some kind of, technically it's an operational semantics, but you can think about it as a non-deterministic interpreter. And then you state a theorem in Coq that deadlock cannot occur. So this took about 13,000 lines to prove. But the nice thing about this proof is that it now applies to all programs that you type check. So whenever you have type checked your program, you get a formal proof out that deadlock cannot occur, which might otherwise be a lot of work to obtain for each separate program. Yeah?
Do the runtime semantics assume any kind of fairness, or it could be any adversarial type scheduling?
It does not assume any type of fairness. If you want to get a stronger property than deadlock freedom, you would need to assume some kind of fairness. But for deadlock freedom alone, it's OK not to assume fairness. Yeah. OK, so now we have seen how to get a deadlock-free type system for locks. I want to now talk a bit about a deadlock-free logic. So let's talk about what that is. So in the programming languages world, you have two sides. So one side is type systems, which you can view as sort of verification procedures that check weak correctness properties. So like in Rust, they check memory safety. Using types, you typically do not get strong correctness properties like my function actually computes the right value. On the other hand, with type system, checking is usually completely automatic, so you don't need to do any manual proof work. Program logics are the other side of the coin, where you do get this strong functional correctness property, but you have to do a manual proof, like in a proof assistant, for example, or on paper, if you like. So the original program logic was the Hoare logic, developed by Hoare. But these days, there is a much more developed literature about it. And probably the most advanced separation logic, which is a version of Hoare logic, is called Iris. And there have been about or I think by now exactly 121 papers on this. But so here I claim that this gives you a strong functional correctness property, but actually this is not really true. So let's now see why that is. Let's give some background on what Iris is exactly. So the people who made Iris, they started building on top of the ROC proof assistant, and on top of that they built Iris. So what does that consist of? Well, first it consists of a way of defining programs in ROC. So you define the abstract syntax tree of your program in this math system. Then you have assertions, which are formulas that talk about your programs. And then using those assertions, you can write Hoare triples. And you can state those as a theorem in the proof assistant. And then there are features that let you prove this theorem. And then after this theorem is proved, this Hoare triple is true. Okay? But then the next question is, what does that actually mean for that Hoare triple to be true? So if you look at the fine details of Iris, the fine print, it says that if you can prove this Hoare triple P, E, Q, that means that if P held initially and you run E, then Q holds. So this is what you would expect. And it says that E is memory safe, so you will not get use after free or any of these other problems. But note that this definition does not say that E does not deadlock, nor does it say that it does not leak. In fact, this is not true. In Iris, you can prove this Hoare triple perfectly fine for E stat deadlock. Okay? So that's not an ideal situation because you thought your program was correct, but it's only correct if it does not deadlock. Okay? So I developed a follow-up on this in which if you prove this Hoare triple, the fine print of the theorem that you get out does say that E does not deadlock and E does not leak. And you might think, okay, now maybe this logic is way more complicated to use than the Iris logic, but actually the rules are quite similar. It is true that this logic is more limited than Iris. Part of that is future work, but for the programs for which it does work, the proof is pretty much as simple as it would be in Iris. So you get these extra guarantees more or less for free. So here's an example of things you can verify with that. So you can implement message passing channels as programs in this language. And you can, for example, then do merge sort using message passing channels. So how does that work? Well, if you want to sort a list, we just send this list as messages through time on this channel. Then we send one more message saying, please, other side, now sort this list. And then you receive messages back, and you expect those to be in order, right? The sort of merge sort, but it's happening in time and not in space. So you can imagine that you can do this recursively. So if you had a procedure that could do this, you could do it recursively by sending all the odd elements to my left helper, sending all the even elements to my right helper, then collecting them back up and merging them in the right way, just like merge sorts. But here, this is all happening in time and interleaved. So this is all a big concurrent mess. But it turns out that a previous proof that people had already done in Iris worked without change in this system. So you just get the deadlock freedom property for free. And note that deadlock freedom is formally, here it's non-trivial, because it could be that this concurrency is happening in a wrong way, such that this whole message passing could deadlock. All right. Let me talk a little bit about future work and what is not done here. So I want to tell you what I think the spectrum of verification looks like. So I think there are three axes to verification. So one is, which property are we proving? So we already saw that Rust gives you memory safety, and this work gives you deadlock freedom and memory leak freedom. So that's a slightly stronger property. You can go even further to the right. For example, you can prove liveness, which is stronger. You can go even further. So liveness says that eventually something good will happen. Type complexity is even stronger, which says within this many steps something good will happen. Then there's a different axis, which is for which class of programs does the verification method work. So the simplest class is sequential programs. For example, the original OR logic worked for sequential programs. And then the systems that I've talked about today work for logs and message passing. And then you can go all the way on the right and, for example, have programs that use fine-grained concurrency like compare and swap. And then below I have this spectrum from automated checking to logic. And you may ask, why have I put that as a line? Are those not incomparable? But it turns out that if you have a sufficiently good enough logic, you can sort of derive a type system from it. If you have a sufficiently compositional logic, you can more or less read off an appropriate type system. So I would say having a logic is better than having a type system in that way. So Rust would cover this area. So Rust proves memory safety. It works for all these kinds of programs, and it falls into the types category. What I've talked about today covers this area. So it goes beyond safety, and it goes beyond types. But it does not support these stronger properties like liveness or time complexity, nor does it support fine-grained concurrency or even some more basic features like condition variables, for example. The logs we have seen so far do not have condition variables. Or even reader-writer logs are not yet supported. So one direction for future work is to try to push this boundary to the right and see if we can cover the whole space. In particular, one big open problem in the Iris world is to get some kind of logic that you can reason about liveness. Currently, no one knows how to do this. But I think some of the same techniques that I've talked about today can achieve this as well. So then I think there's even a very different axis. So what we have talked about today is to increase in the vertical axis to increase correctness. So we start with Rust, which only has safety, and we go up and try to get more correctness properties. And we can get even more of them, potentially in the future. But I think also a very interesting direction is the horizontal axis to try to make Rust more usable. Because I think one of the main complaints that people have about Rust is that its type system is rather hard to use. So you could think, okay, then we can switch to Python. But and in general, we could try to go into the right corner. But I want to ask the following question. So what is to Rust as Python is to C? So one common mode of programming is to implement your low-level libraries in C and then use them from Python. So can you do the same thing with Rust and Python? Actually, it turns out you can't, because Rust needs to maintain certain invariants which are violated by Python. For example, Python can introduce aliasing in Rust data structures if this is not explicitly checked everywhere. So one question is, can we develop something that creates the same kind of pairing between Rust and that thing that Python and C have? So currently this doesn't exist. So I think the key Rust enabler is this property that you have aliasing or mutability, but not both. So let's look at what that enables here. So if you write any function foo in Rust, let's say this foo here, which takes two vectors as arguments, if you now modify y, let's say you increment y0, this is guaranteed to not affect x. Note that this is not true in Python. In Python, if you write a function with two arguments and you increment one element of y, you may have aliasing between x and y and have this modify both. And I think this is really the key enabler of Rust that makes the whole system work. So the Rust strategy for this is to say, OK, if we think there could be aliasing, we just give the program an error. For example, if we have a nested vector right here, and we call this function foo with yi and yj, then the Rust type system is going to think, well, if I is equal to j, there's an alias, so it's a problem. So even this potential alias is going to raise an error. Okay. So the disadvantage here is that you have this heavyweight type system, which is imprecise, and it also breaks abstraction, by which I mean if you take any piece of Rust code and you try to extract it in its own function, that is sometimes not possible because of the borrow checker. So we would like to have a language that's like Rust, but feels more like Python. So let me describe a strategy that I think will work, which is actually pretty simple, which is to do the following. So if we detect that there could be an issue, just make a copy at that point. But only do the copy when it was really needed. So in this case, what you would do, if I is not j, then you can just pass these things in as in Rust. If I is j, then you would have to copy y. So, yeah?
It's like a lazy copy on alias?
You could imagine a version in which you copy eagerly, but copying could also mean copy on write, for example. What copy actually means is left unspecified here. So in this case, yeah?
Doesn't it change the semantics of the program to copy in the example you showed?
Yeah, it does. And I think that's a good thing.
But what, I mean, yes, you've got us excited now. why not just abort if I equals j? I mean, just fail. I mean, it seems to me that making a copy now is so sort of brittle, especially if the programmer had never expected I to equal j. I mean, it's hard to know what poison to choose here.
Yeah, maybe, but I think this strategy is better because so I think usually you do want a copy here. Like here, you passed in y as an immutable argument, so you expect that thing to just be whatever y was at the beginning. So I think that's the right strategy here. But yeah, so in this case, the borrow checker becomes more like an optimizer or a linter. So the borrow checker could still give you a warning if you wanted to, but I think this would enable you to have a more high-level programming language. Note that, for example, in Python, this kind of people don't care about this at all. So you just keep running the program and do something that's completely wrong. Okay, so why do I think this? Yeah, go ahead.
What you want to express about this copying, is it that when a Rust programmer wants to write this, he would basically just do the clone manually, whether I equals to j or not, but now you're just saying we can save that copy when I equals j. Sorry, when I doesn't equal to j.
We save the copy, plus we don't have the whole type system. We don't need the whole type system anymore. You can, it would feel more like Python than Rust.
I see.
But you're giving up, now the runtime system is going to pick up the slack. But
Yes, yes, for sure, yeah. But what this would enable is you to have safe interop with Rust, because now the high-level language maintains the same invariance that Rust does. So now you can directly pass data structures between each other. You do not have this, have to have between these two layers alias checking all the time, okay? I think this would also give you the opportunity to do better optimization. For example, a language like this allows the compiler to choose a more efficient memory representation. So in a language like Java, you have pointers everywhere. Let's say you have an array of mutable point objects. Points are, let's say, an object with an x and y, floating points. The Java compiler cannot eliminate this pointer indirection there, because if there's an alias, it would need to maintain the right semantics. Whereas in this language, that never happens, so you are more free to choose any data representation you like. In particular, the same one that Rust uses. Another thing is, I think it would allow the compiler to more easily reason about code, because you have this the same property of Rust, which says that if you modify one variable, you will never modify another. So you can reason about this code more or less like you could reason about a purely functional program. In fact, you could translate this program to a purely functional program. Okay. And that's why I got really excited about it, because in that case, you could use this language as the basis of a proof system. So you could build a proof system like Rock, but instead of you having a purely functional language at its core, you could put a language like this at its core. and then have a very nice verification methodology which works very well in Coq, but write in a more sensible language than in the purely total language of Coq. Okay. And why do I think this will be important? Well, I think more and more people are going to have AI write their code. And I want to create this system in which AI will also write the proofs. So it will also verify your code for you. I think that's unrealistic in conventional languages. Let's say you write a Java program. I think it's very unrealistic to do completely automated proofs there because you need very complicated constructs like separation logic. In such a language, you can reason about it just as you can about Coq. Okay, so to recap, we asked ourselves what will be in this next blue bubble. So I think there will be two directions there that are important. One is to get more correctness properties like memory leak freedom and even stronger ones. Another one is to get more usability. And I think at the end of the day, they will even interact because if you have Rust at the lower layer and this other language on top of it, you also want to verify interaction between those two languages. So all the theory about separation logic is still relevant if you want to check this interaction, especially if you write unsafe code in Rust. So it all forms one coherent whole. But to actually make this work, you need new research, just like the research originally influenced Rust. So today I have presented these two papers here, dialog-free locks and dialog-free separation logic, but I've done a bunch of other work, also, for example, on automated reasoning. So if any of you want to talk about whether we can collaborate on that, I would be very happy to hear. So the key takeaway here is that I think that you can get extra leverage if you can co-design your language with formal reasoning methods. So instead of taking an existing language, trying to verify code there, if you give yourself the freedom to change the language a little bit, you can make your life much easier and go much further in terms of verification. That's it. Thank you.
One of the things that has also made Rust really popular is how good its optimizer is. And one of the reasons the optimizer is so good is because it's taking advantage of these invariants from the type system. When I add in deadlock and memory leak freedom, are there any additional optimizations that become possible? Or are these invariants that are just about not going wrong that don't really help the optimizer so much?
I can think in theory that there would be optimizations that would be possible. For example, now you know for sure that for every object its destructor gets called. Maybe you can get some leverage out of this. But in general, I think it's not as useful for optimization as the no aliasing restriction is.
What about failures? So, you know, we have message passing, but there's no drops, dupes, corruption.
Yeah.
Do you think these are things we can also pull into the type system?
It depends what the reason for the failure is. If the reason for the failure is some complicated reason, you would need a verification, manual verification to establish that this failure doesn't happen. Let's say you implemented some algorithm, you expected some invariant to hold. You panicked in a case that you didn't expect to reach. That would require manual verification to make sure that it doesn't happen. Yeah, I don't know. Maybe you have a more concrete scenario in mind that you could check.
Oh, I was just thinking of some things James did in Verdi, and some things Halbin did more recently in Ironwood, and you know, how easy could they be? You know, there's this kind of jump from message passing concurrency to distributed systems that involves failure. And so I guess I was just thinking about failure broadly. Or I think there's some old work by David Walker and co. on transient faults, you know, random bits that get flipped as we keep shrinking feature sizes in silicon. Maybe that will get worse, and I was curious like how that could be captured with some of the techniques you were describing.
I think if you can detect the failure, then it could be easily handled because you just make the API such that if you do a call, you may either get a failure or not a failure. In that case, it could be incorporated, I think. If you have transient failure or failure at the hardware level, it seems harder to integrate that with a type system.
I can keep going all day, folks, but
No, I got it. In the old-fashioned way of dealing with deadlocks manually, debugging is hard, but usually it's hard because we don't know the thread schedule. And once we know the thread schedule, actually seeing the cycle of lock acquisitions is somewhat tractable, understandable, even amenable to tooling, perhaps. Have you looked at, debugging the type errors that prevent, in your system, how people struggle with them? Is it because of false positives? Is it because just type error messages are hard? What's the static debugging story?
So I think it depends on how you implement it. If you do this automatic set solver technique, it may be hard to tell exactly why the verification failed. But you could then manually annotate spawn calls, and then it would be clear why it failed. If you want to have it all automatic, then it may not be very clear why it failed. But there is a sort of a smooth ramp to trying to understand why it fails, just like with type inference.
Well, let me see if this makes sense. Let me see if I understand the answer. That if you're doing somewhat explicit typing, and it's really only spawn that gives you choice, you learn the rules, you see where the rule wasn't followed, you're done. But if you do the implicit approach, throw it at the SAT solver, you have this combinatorial explosion as you have multiple spawns. And now, the fact that none of them worked is not necessarily easy to see.
I think it's still okay if you annotate each of your function at function boundaries. Then at least the solver would only operate on a delimited area, so you might still be able to understand it in that case. If you wanted it to globally infer, just like with ML in the Milnor type inference, it gets hard to understand the type error. What you do then is you just add more and more annotations until you see where it goes wrong.
So getting back to the annotations, are there, standard design patterns or so on that would suggest that there's a particular choice of how to pass things through at the, make these decisions at the spawn? Is there just sort of a rules of thumb for programmers to how to do those annotations that you think?
I think typically it's common to keep ownership in the main thread. It sometimes happens that you want to give ownership to the child thread, but this is actually rather rare. If you have a lock that you have not yourself acquired, there's no choice. There's no crown, no key, so they just keep going. So sort of in most cases, you don't need to do anything. Only in the case that you have acquired a lock, you need to decide who gets the responsibility to release it, the child or the main. And I think usually if you write your code, it's pretty clear what you intend. For example, if you want to do a fork join type of approach, then the child gets the responsibility to release because it has to put a value back in that you will get out in the main thread.
So in this context, would it, in some sense, make sense to have variant names for these spawns that sort of force the programmer to choose?
Yes, you could just have all these, I don't know how many I had, 9 or you could have different names for all the variants. The main problem is if you have a lock group in the full system, there are an infinite number of different spawns. So in that case, that strategy wouldn't work.
So I actually have a follow-up question on Dan's question. So I think, let's say I have a program that does not type check. Is there a way for the user to debug the program by relating this type checking failure to some kind of operational counterexample that actually shows a program trace? that why this program can lead to deadlock or memory leakage.
Yeah, currently we don't have a method to do this, but it would be interesting. For example, let's say you pass 2 locks and you use the wrong lock order. Yeah, it would be interesting to figure out, is there some kind of schedule that actually leads to some cyclic wait? And maybe the actual lock order violation could give you some leverage on how to construct that schedule, because you know that they will need to happen in a certain order in that case. But yeah, this would be interesting research.
So in the first part of the talk, you talked about the deadlock-free and leak-free extension, and then at the end you pitched this like analog to Python. So
Yeah.
I'm wondering if you had Rust interrupt between the high-level language and Python, can you have concurrency across that language boundary where you spawn a thread from the high-level language that then does something in the low-level language, and maybe one of them acquires the lock and the other one releases it? And how does that, what's the mechanism for crossing the boundary there?
I think there are 2 options there. Either you check dynamically that things are okay, or you add the same type system to your high-level language side. Note that you still don't need a borrow checker in that case. So yeah, I think those are basically the 2 options you would have. But yeah, it's an interesting question, interesting to think about.
Maybe, I don't know. Do I need the mic? Maybe I need mic, I don't know. So a more wide-ranging question on the Python language idea. In some ways, it reminds me a little bit of Fortran, in that one of the fantastic things about Fortran is the way it does arrays tends to remove a lot of the aliasing concerns you have in C.
Yep.
I was wondering if you could comment on that. Maybe I'll spice it up. Did we go completely off the rails with C and C++? And if we just stuck with Fortran, everything would be great.
I think actually C++ works in a similar way. In C++, by default, if you pass in a vector, it just copies it. Or yeah. So, well, you don't want to do it completely naively, but I do think it's ultimately the right approach.
Yeah.
Oh, yeah. So also for your first part of the talk, so basically you introduced an ownership system for logs. So that's why like your logs are acyclic basically. But this also prevents you to represent data structures like DAG. So have you think about like how to cover these cases?
If you have a DAG, it's more difficult because so the difficulty with a DAG is that it's hard to prevent 2 people from getting it's hard to prevent people from getting 2 references to the same thing, because if you have a split, the type system would allow you to dereference both ways. But if now those are 2 totally independent variables, so if they then point to the same object, you can obtain 2 references to the same thing. So handling DAGs in general is difficult in this case. So if you want to handle DAGs, I think you would need some manual verification, or just give up and getting leak freedom for that part. Note that it's fairly uncommon to store logs in DAGs, for example.
Any other?
Yeah, great job with the talk. I was wondering if you had a bit of a sense of the ergonomics of your type system when applied to practical algorithms that you might learn from like a textbook. Like, do you have a sense of if those are easy to implement with this type system? If you want to blend it with like a typical Rust library like Tokyo or something, like would that also cause a problem, or does it kind of come for free?
I think in practice, how people use logs and message passing is usually very simple. So in many cases, even this type system is sort of covers way more than practical use cases. But then there are some cases in which things are hard. For example, that logs are acquired in the right order, depends on some runtime data and requires some higher level reasoning to make sure that it goes right. And in that case, this system is insufficient. You would need something like dependent types in that case, or some other verification methodology. So I think there's sort of two regimes. One regime is it's just easy, and then you can get your deadlock freedom and leak freedom from this system. In another case, it's really hard, and you need to do manual verification.
Well, if we don't have any more questions, let's give another